In this video, we learn how to evaluate triple integrals in spherical coordinates. So instead of the usual x, y, and z Cartesian coordinates, we can use another triple of coordinates, which are called the spherical coordinates, to specify a point in 3D space. So the way we obtain these spherical coordinates, if first we look at our x, y, and z coordinate system, is to introduce three numbers instead of x, y, and z, and the three numbers to specify a point in 3D space are the distance from the origin, so that's the first coordinate. The distance from the origin, let's call this distance rho. Then the second coordinate is the polar angle that we used in polar coordinates. So we project our point to the xy plane and look at the line segment connecting the origin with that projected point P prime, and the angle that it makes with that line segment makes with the positive x-axis will give us the second spherical coordinate theta. And last, we look at the angle that the line segment connecting the origin with our point P makes with the positive z-axis, and we call that angle phi. So these are the three spherical coordinates, r, theta, and phi. So it's a different way of generalizing the polar coordinates to 3 dimensions. The cylindrical coordinate system was one way of doing it, where we kept the polar coordinates and where we had the polar coordinates in the xy plane and then kept the z coordinate from the Cartesian coordinate system. Now we have the polar coordinates in the xy plane and then use this angle that it makes with the positive z-axis as our third coordinate. So let's just try and come up with the formulas connecting x, y, and z with, sorry, I should have written rho, theta, and phi. So let's start with z perhaps. So what's the height of this point? So if I know that the distance from the origin is rho, and this angle is theta, sorry, this angle is phi, then so is this angle, it's the same angle phi. So here I have a right triangle with hypotenuse rho and an angle phi. So this leg of the right triangle is going to be rho times the cosine of phi. Okay, by trigonometry, basically the cosine function is being used. Now the other angle, which is the distance of the projected point from the origin, will be rho times the sine of phi. Okay, and now all we need to do is look at this right triangle, connecting the origin, the x-axis, and this projected point, because this angle right here is theta, and we know that this hypotenuse is r times the sine of phi. So we can now figure out the x and y coordinates to be the cosine of theta times the length of the hypotenuse. So let me write that as rho times the cosine of theta times the sine of phi for the x coordinate. So that's just that. For the y coordinate, we have the sine of theta times rho times the sine of phi. Okay, so the sine of theta multiplies the length of the hypotenuse to get this leg, the y coordinate. So this is the length of the hypotenuse, and sine of theta multiplies that. And we've already found the z coordinate to be rho times the cosine of phi. So these are the formulas that connect the Cartesian coordinates to our spherical coordinates. And next, in order to formulate the triple integral formula in spherical coordinates, we need to think about what happens to the volume element when we take the triple Riemann sum and that small spherical rectangle as we take these small changes in rho, theta and phi. So let's try and sketch that out. So let's imagine that we are at some point with coordinates rho, theta and phi in 3D space, and then we add delta rho, delta theta and delta phi to form a spherical rectangle. So what happens when we take this point and add delta theta to our coordinates? Well, if this is theta, adding a small delta theta will take us that projection. So that of course corresponds to some point there. Here we have a circular arc, okay, whose radius is just the same as we had here. So what's that radius? Well, that's rho times the sine of phi. Okay. So that's the radius, and this angle right here is delta theta. Okay. So now we have this change in theta. Let's change now phi. Add to phi, this is the angle phi, add to that delta phi. So that will take us from here down to here, let's say. So that's delta phi. Okay. So this length, of course, is rho. So again, we have these edges. Okay, and finally, let's add a delta rho to our rho coordinate. That will take us away from the origin by an amount of delta rho. Okay, so let me now try and draw this box. It's not very nice, but the idea is that now we have a spherical box whose sides are, well, that side right there is delta rho. This side right there is rho times the sine of phi times delta theta, because we have this circular arc with radius rho times sine of phi, and the angle is delta theta that corresponds to that circular arc. So that length is this quantity. And finally, the third length is right here. So that length is rho, is the radius that we have there, and that's a circular arc with radius rho and angle delta phi. So that's going to be rho times delta phi. So these are the three edges of our spherical box. So the volume, the change in volume that the spherical box makes when we have these small changes in rho, theta and phi is the product of these three quantities. So you see rho appears twice, so that's rho squared. Then we have sine of phi, and then the three small changes in rho, theta and phi. Okay, so this is the important bit, because this is what turns into the volume element, and it's very important that when you change from Cartesian coordinates to spherical coordinates, it gets an extra factor of rho squared times the sine of phi. Okay, so let me now look at the triple integral formula in spherical coordinates. So let's imagine that we have this triple integral of a function where first I integrate with respect to phi, so let's say that phi changes between C and D, theta changes between alpha and beta, and R changes between A and B. So if this is, well, let me just first have the triple integral written as usual. So we have the triple integral over some region of a function x, y, and z, of a function of x, y, and z times this volume element. So this is the integral when phi changes from C to D, rho and theta changes from alpha to beta, and rho changes from A to B, of f. So remember, x, y, and z are these expressions in terms of rho, theta, and phi. So it's rho times the cosine of theta times the sine of phi, that is x. Rho times the sine of theta times the sine of phi, that is y. And finally, rho times the cosine of phi is z. So this is the function evaluated at x, y, z in spherical coordinates. Then we multiply this function by rho squared times the sine of phi, and then integrate with respect to rho, with respect to theta, and with respect to phi. Okay, so this is our triple integral formula in spherical coordinates. And remember, this factor of rho squared times sine phi is very important not to forget, because that's what makes the formula correct. When we change from Cartesian coordinates to spherical coordinates, it picks up an extra factor of rho squared times sine of phi. So let me give you a question. Let's evaluate the triple integral of the constant function 1 over the unit ball. Sorry, not the unit ball, but the ball centered at the origin and of radius r, whose inequality is given there. X squared plus y squared plus z squared is less than or equal to r squared. The points in 3D space whose coordinates satisfy this inequality form the solid ball of radius r, centered at the origin. So compute this triple integral using spherical coordinates. Pause the video and input your answer below. Okay, I hope you paused it and basically just applied this formula with, of course, remembering that, okay, here we have a ball of radius r, so that means that rho changes from 0 to r. That's the distance from the origin. As we go from the center of the ball to the surface of the ball, rho changes from 0 to r. Theta, the polar angle, can change between 0 and 2 pi, so takes all values, rotates around as we go around the ball. And finally, phi can take any values between 0 and pi as we go from the north pole of the ball down to the south pole of the ball. Phi will take every angle that it can take, so between 0 and pi radians, 0 and 180 degrees. So these are the boundaries for our variables. So what it means that if we take this formula, C will be 0, D is 2 pi, alpha is, D is pi, alpha is 0, beta is 2 pi, and finally rho, well, A is 0 and B is capital R, is the radius of our sphere or of our ball. And now it's the constant function 1 that we are integrating, but remember, it picks up when we go to spherical coordinates, we get this extra factor of rho squared times the sine of phi. Okay, so and this we have to integrate with respect to rho, theta, and phi finally. So what we are doing is, well, evaluating, integrating with respect to rho will give us rho cubed over 3, as rho changes from 0 to r. Then we, of course, still have to integrate with respect to theta, sine of theta factor, sine of phi factor is important. So theta and phi. Okay, so what this gives us, this change is giving us capital R cubed over 3. So capital R cubed over 3 is what we are evaluating, what we are integrating. It's a constant in both theta and phi. So when we integrate with respect to theta, again, the sine of phi does not depend on theta, so that gives us an extra factor of 2 pi when we integrate that. And finally, all we need to do now is integrate with respect to phi, sine of this multiple of sine of phi, as phi changes from 0 to pi. And so this is just, as you may remember, we are integrating, well, let's forget about these constant factors for the moment. We are integrating the sine of phi as phi goes from 0 to pi, so that's the area under the sine curve as it goes from 0 to pi. So one hump of the sine curve has an area of 2, but you can, of course, evaluate this integral properly as saying like this is minus the cosine of phi as phi changes between 0 and pi. And this, of course, evaluates to minus 1, so that's plus 1, minus 1, so that's another plus 1, so this gives you 2, a factor of 2. So if you put all these together, what you get for this integral, and it's kind of important, for the ball of radius r, capital R, what this gives you, if you multiply 2 by 2, that's 4 pi over 3 times r cubed. And that is exactly the volume of a sphere of radius r. So that's exactly what we just computed. Okay, I hope you enjoyed this video, and I'll see you in the next one.